Thank you, David, for putting together the event, both of you, of course. And today I'm going to talk about my research, which is covering context detection using mobile devices, primarily with smartphones. You all carry it in your pocket. And I know this is a very dividing topic. We had previous meetups where we're raising awareness of how dangerous it is to upload so much data into the cloud and what that can lead to. But at the same time, we cannot neglect the benefits that we get by taking advantage or leveraging the sensor data we can collect with our devices. So I hope that my research is going to bring a bridge between these two aspects. So, yeah, a few key takeaways from this presentation would be that sensors on smartphones and wearable devices in general are useful to detect very complex user context. And some of the contexts that I'm going to talk about are indoor localization, indoor-outdoor detection, and activity recognition. And finally, I'm going to conclude with a vision of how context detection can be used in real-world applications. Okay, but first quiz for you guys. This is the representation, the signal of acceleration from a smartphone. Do you know what activities this represents?
Running, jogging, walking.
It's walking, yes. The bus? Is it? No, it's actually walking, indeed. What about in this case? And don't think just as activities themselves, it can also be the signal received from other interactions around the users, other physical phenomena happening. So, do you know what this one would be?
Is it volume, noise?
No, it's the signal from accelerometer.
So it's a car?
Car? No, close. So it is indeed a transportation vehicle? Nope.
Bike. Bicycle.
Nope, nope. It's actually the elevator. Exactly, it's a transportation mode. When the elevator starts going down, you have a descending peak of the acceleration when the elevator starts, or the lift, when the lift starts moving until it reaches a constant speed here. So first it accelerates, in this case it decelerates because it's going downwards, and then coming to a constant speed while moving between floors. So looking at the distance between the peaks, you can actually determine the number of floors that the user has traveled. And of course, you can have it, yes, so it's the elevator going down, and you can have it in the opposite direction when the elevator is going up. There are a lot of noises there's a lot of noise when the elevator starts moving, but that can be easily filtered out. This is the raw signal from the accelerometer. Okay, what about in this case? This, to give you a hint, it's actually when the user is climbing stairs, going up and going down. Well, do you know which one is the top one?
That one?
So is this going, it's when the user is climbing?
Yeah.
And this one is when the user is climbing down, going down the stairs. Well, to be honest, I don't know that myself either. But apparently there's enough information in the signal for a computer to accurately detect which one is which. So yeah, in this case it's when the user is going up, you're right. And this one when the user carrying the phone is climbing down the stairs. Okay, but the final quiz, the last one, and I promise it's the last quiz. Do you know which activity this one is? It's a bit more complex.
Hang gliding?
No.
Bungee jumping?
What if I add an extra signal? This would be the heading of the user. You can see it starting from, you can detect this with the magnetometer, and it's the orientation of the user, starting from 150 degrees, then rotating to 250, and then coming back.
Is it driving?
No. It's actually the activity of going into a room and rotating around the door where the user is. So you can see you can get more clarity by adding additional signals. So not collecting just the accelerometer signal, but also looking at the heading and the orientation of the phone while the user is performing those activities. Okay, that's enough with the quiz. Now to get into the real business. Quick background about indoor localization or location altogether, so how it started. Even from the old days, people wanted to know their position. They wanted to know how to get back from hunting, for instance, or they wanted to know their position in the universe, so they started mapping the stars in the sky and how the Earth rotates around the stars. So we've always had the tendency to map our surroundings. So cartography started actually 1,500 years ago. We don't know if it's exactly when it started, but that's the oldest map we have nowadays. So it represents the city of Nippur in Babylon. And you can see here the river flowing or the walls of the city and some structures, physical structures on the map. So it's fair to say that it's safe to say that we've always had this tendency of localizing ourselves. But before the GPS era, how was navigation done outdoors? Starting with Navtec in 1985, and Fred here confirmed the information that I dig up, being one of the first employees of the company. They started digitally mapping the environment for navigating inside of a car. They were basing their information on gyroscope plus compass system that would estimate the orientation of the car, and also a way of measuring the distance that the car is traveling. And in that case, you would get corner by corner orientation in the city. For instance, if you wanted to travel from the airport to the hotel, you would get this information printed out at the airport, and they will give you indication of how to reach your destination. Imagine going into a new city and not having any other source of information. And another important aspect is they were also collecting some reference points, usually by image description. This means that they would add additional information, kind of like you have a coffee shop on your right or a shopping mall to your left, so you don't get lost. So occasionally you would want to reassure yourself that you're on the right track. This is an important concept because I'm going to come back to it later when I talk about indoor localization. But nowadays, mapping it's easy with Google Maps. They have a simple interface, and they also provide location based on Wi-Fi fingerprinting. Though it's safe to say that it's not very accurate. It has a range of around 40 meters. This is actually the informatic for the building that we are in right now. So you cannot actually tell where in the room you might be, in which of the room. With 40 meters, you can be anywhere in the building. So imagine the scenario where you want to navigate through the aisles of a store, supermarket. You want to find sugar on aisle 5, for instance. Sorry. Using Google Maps, that's currently not possible. Or the same situation could be with finding a book on the shelves in a library. So what solutions do we have to get past to get even greater accuracy for localization? We have two current solutions, pedestrian dead reckoning and Wi-Fi fingerprinting. Very short way to describe what they both mean. So pedestrian dead reckoning, you start from a known location, and with a way of estimating the heading, the direction of movement of the user. This could be either from the compass, because it's accurately grounded in the Earth reference frame, and also assisted with the gyroscope. You can accurately get this estimation. And also finding a way to estimate the distance that the user is traveling. if you remember, the activity of user walking represents kind of like a sinusoidal signal. So you could easily impose a function on that. So count how many times the signal go past 0, and that will represent each time a user is performing a step. And having access to these two estimations, you can estimate the consecutive position and perform the same inference. You would have continuous estimation of the location. So if it's that simple, you would just start easily from this point, travel in a straight line, and end up at the corner. But in reality, it's not that simple. This is what you usually get in practice. And that is because you have additional interferences in the environment. In this case, you see a high radiation, which is caused by a magnetic door in this position. This has the effect of deviating the compass, and even if you combine it with the gyroscope, so fusing the two sensors together, the gyroscope is reliable on short periods of time, but it also accumulates error. The sampling is not always perfect, and you can think of the gyroscope as being a similar process with that reckoning. You build on top of previous estimations. And once you introduce small errors, those tend to build up and your estimation goes way off from the right trajectory. Okay, so what would be the solutions in this case? Relying on, as we were mentioning earlier, you can detect the user's activity. So knowing where the position of the elevators are and the stairs, you can use those reference points to recalibrate the user's position. So determining when the user is performing particular activities that are accurately localizable on the map, you can recalibrate the user's position occasionally. And also relying on Wi-Fi fingerprinting. A very short description of what this means is when you have your phone scanning the Wi-Fi environment, it can determine the access points that you see around you and the signal strength that they're received by the phone. And you can imagine we're collecting a lot of measurements from exhaustively in this case. You would just go cell by cell and get the exact measurements on all those positions, and thus creating a database of Wi-Fi fingerprint location pairs. And at runtime, you would just compare your current observations with the database, thus finding out the location where the user might be. I'm getting very much into technical details here, but I'm going to leave this description. If you're interested, you can find it in the paper. You can find everything is available on my website, open access. But a very quick description of what it does, and combining all the sensors with activity recognition and knowledge of where those landmarks are in the building, as well as Wi-Fi fingerprinting, combined with particle filters to get a single estimation, which is more reliable than those doors, whereas the white represents outdoor. So you can have a situation where the signal from the GPS is received inside of a building, whereas outdoors, when you're in areas with very tall building called the urban canyons, you won't receive a good signal, and that's how the system can get confused. It's not very accurate, and at the same time, it's a very energy expensive sensor. You probably know if you let them just on Google Maps and drain your battery very, very fast. What about reliability? New labels for the system, which means that you can have the system continuously training itself. And our performance was in the 90% accuracy, surpassing all the other systems before us. Cool. And the last context that I'm going to talk about is activity recognition, but this time using a different architecture. This is based on deep learning, and we're using two modalities in parallel, in this case accelerometer and gyroscope. With deep neural network on each of the modalities, you would extract preliminary features, which can then be combined to come up with a single estimation. So our observation is that pre-selecting those features by the network independently on each of the sensing modalities is more efficient than just putting the data all together into a single architecture. That is because one of the sensors may dominate the other, and you miss out important information from each of the sensors if you don't allow it enough space to extract its own features.
Valentin, a couple more minutes.
Okay, yes,
Yeah.
I'm getting close.
Okay, good.
Just very fast, the evaluation for this system, we had the large data set, 9 participants, each of them were performing 6 activities with 8 devices, and we surpassed the previous classifiers. Ours was in the 80%. You may say this is very low, but actually the training was done with a method of leaving one of the participants out and training on the rest. So this resembles kind of like a fresh system for the other user. Imagine you're developing an application and you want to release it and be used by a lot of users. So you don't have label data from all the other users. But the observation is that if you specialize the network on the users later on, you can reach 95 to 97% accuracy on those users with less than 5 minutes of additional training data. Okay, the energy efficiency we evaluated with the development board, the Snapdragon, the processor very similar to the one you have in smartwatches and the older generation of smartphones, just to have full control over the measurements. And what we found was the impact of energy consumption on a battery, on a typical battery on a smartphone is less than 1.2% of the whole battery for this sort of inferences and sensor sampling, just because the sensors are much cheaper than the GPS and all the other sensors. Okay, so getting close to conclusions. Why is this important? We have a debate nowadays that moving our data into the cloud and helping our services is beneficial to us. But with such a system, you have everything under control. You produce the data locally, and you also consume it locally with specialized context detection algorithms. In this case, you don't need to transfer a large volume of data to the cloud. So you have nowadays the problem with Amazon Alexas. The police is trying to get access to their to voice data from one of their users in California because of a crime scenario. So you can actually see how harmful it can be to send your personal data to the cloud. But performing all the inferences locally avoids all these problems while still taking advantage of useful inferences to assist you throughout the day. Okay, so the vision is that many inferences will be performed locally on mobile devices and wearable. So we will have more and more of such inferences happening on our devices. The default setting should be off for uploading the data. Everything should happen locally to the device. If you want to improve the algorithms and the architecture, the deep neural network architecture, then you'll have to give some incentive to the users to upload their data. That can be cash or discounts next time you're selling them something. Think of bus companies, they'll give you a discount next time you're purchasing a bus ticket. Finally, arrangements to prepare or signal your house to put on romantic music and turn on the lights. At the same time, you can also instruct your personal robot to start cooking your favorite meal to be ready once you arrive at home. So I'm going to leave you with this question. What interesting and useful context detection can we think of to improve our life? Something that can happen on the phone with the sensors we have available for that. Thank you. Oh, sorry, before that, I need to acknowledge my collaborators, my supervisor Mahesh Marina, Lito, Yota, Rick, Nick, Surav, and Cecilia. That's it.